As with lists, we can locate stack elements by index. The index starts at 0 for the top element and increases by 1 for each element that follows. For example, suppose that stack S is 11, 7, 3, 19. Then the element at index 0 is 11. The element at index 1 is 7. The element at index 2 is 3. And the element at index 3 is 19. The statements above describe the indexing operation for stack S. We can cover all stacks of length 4 by replacing numbers with variables. For example, the element at index 0 of ABCD is A. The element at index 1 of ABCD is B. The element at index 2 of ABCD is C. And finally, the element at index 3 of ABCD is D. As we can see, we need 4 properties to cover stacks of length 4. Following this pattern, we will need 5 properties for stacks of length 5, 6 properties for stacks of length 6, and so on. We will need a lot of properties to cover all possible stacks. We can reduce the number of properties needed by making a small modification. Consider the following statement. The element at index 0 of A remainder is A. If remainder is the stack BCD, then this statement is exactly the same as the first of the 4 properties. But we don't have to limit remainder to stacks of length 3. Suppose remainder can be stack of any length. Then the statement tells us that the element at index 0 is always the top element, regardless of the shape or size of the stack. Let's try the same trick for the other indexes. The element at index 1 of AB remainder is B. The element at index 2 of ABC remainder is C. The element at index 3 of ABCD remainder is D. We were able to reduce the number of properties to 1 property per index. Unfortunately, the range of index values is infinite, which means we still need infinitely many properties. Is there anything else we can do? When properties are difficult to formulate, a good strategy is to describe the operation informally first, then try to massage the description into properties. For example, let's try to describe how we can retrieve the element at index 2 of the following stack, 3, 19, 23. We start from 0 and count as we move from one element to the next. When the count is 2, we retrieve the current element. Instead of counting from 0 to 2, we can also count backwards from 2 to 0. Then, when the count is 0, we retrieve the current element. Let's designate the top element of the stack as the current element. We're going to move to the next element by popping the stack. The pop operation removes the top element, making the next element the top element of the stack. The table below shows this algorithm in action. In each step, the index is decreased by 1 and the stack is popped. When index is 0, the top of the stack is 23. Therefore, the element at index 2 of the stack 3, 19, 23 is 23. Notice how at each step we perform the same 2 actions. We can describe this process by writing the current operation in terms of the next operation. Here's an example. The element at index 2 of 3, 19, 23 is equal to the element at index 1 of 19, 23. Let's check whether this is true. The element at index 2 of 3, 19, 23 is 23. The element at index 1 of 19, 23 is also 23. So the two expressions are equal, and the statement is true. Similarly, we claim that the element at index 1 of 1923 is equal to the element at index 0 of 23. We also know that the element at index 0 of the stack is always the top element, regardless of the stack length. Thus, we know that the element at index 0 of 23 is equal to 23. Let's summarize this process as two properties. The element at index I of stack xy is equal to the element at index I minus 1 of stack y. The element at index 0 of stack xy equals x. Property 1 claims that we can decrease the index by 1 and pop the stack without changing the outcome. Notice how the stack changed from xy to y. Property 2 claims that the element at index 0 of a stack is always the top element. Let's use these properties to show that the element at index 2 of stack 3, 19, 23 is equal to 23. Property 1 allows us to claim that the element at index 2 of stack 3, 19, 23 is equal to the element at index 2 minus 1 of stack 19, 23. 2 minus 1 equals 1, so the above claim becomes the element at index 2 of stack 3, 19, 23 is equal to the element at index 1 of stack 19, 23. We can also claim that the element at index 1 of stack 1923 is equal to the element at index 1 minus 1 of stack 23. 1 minus 1 is 0, so the above claim becomes the element at index 1 of stack 1923 is equal to the element at index 0 of stack 23. Now index is 0. And we can use property 2 to make the claim that the element at index 0 of stack 23 is equal to 23. Then, using the transitive property, we claim that the element at index 1 of stack 1923 is equal to 23. Again, using the transitive property, we finally claim that the element at index 2 of stack 3, 19, 23 is also 23. By defining the current operation in terms of the next operation, we were able to describe an algorithm that performs an operation on every element in the stack. We will see this pattern in virtually all collection operations.